14 billion miles from where you're sitting, a machine the size of a small car went silent. No warning, no error message, no countdown. One moment, a razor-thin radio signal was crossing interstellar space, arriving at a dish in the Mojave Desert 45 seconds slower than light should ever feel patient. The next moment, nothing. Static, empty carrier wave, no data, no confirmation the machine was even still alive. Somewhere in the room where that signal was supposed to land, an engineer looked at a screen that should have been full of numbers and saw a flat line instead. Nobody said anything for a moment, because everyone in that room understood the math. If the spacecraft's antenna had drifted even a few degrees off target, out here, at this distance, it might never find Earth again. This is the real story of what happened to Voyager 2 in the summer of 2023, and the 42 days that followed, when humanity's most distant working machine went quiet, and nobody knew if it was coming back. Voyager 2 launched on August 20th, 1977, 16 days before its twin, Voyager 1. Both spacecraft were built by NASA's Jet Propulsion Laboratory in Pasadena, California, on a budget that, adjusted for inflation, would barely cover a modern blockbuster movie. Nobody expected this. Nobody expected either spacecraft to survive past the 1980s. They were designed for a 5-year mission, a single grand tour past Jupiter and Saturn, using a rare planetary alignment that happens once every 176 years. Voyager 2 did something no other machine has ever done. It kept going. Uranus in 1986, Neptune in 1989. Then it kept going past that too, out through the Heliosphere, the bubble of charged particles our sun blows around itself, and in November 2018 it crossed into interstellar space. By 2023, Voyager 2 was 12.3 billion miles from Earth. Its radio signal, traveling at the speed of light, took over 18 hours to arrive. Its transmitter puts out about 22 watts, roughly the power of a refrigerator light bulb, spread across a distance so vast that by the time it reaches Earth, the signal is measured in units so small they barely register as energy at all. And it still worked. For 46 years it worked. Then, on July 21, 2023, a routine command sequence was sent to Voyager 2 from the Deep Space Network. It was meant to make a minor adjustment to the spacecraft's onboard antenna pointing, part of standard maintenance to keep the high-gain antenna locked on Earth as the two bodies moved through space relative to each other. Something in the sequence was wrong. The command tilted the antenna 2 degrees off its target. 2 degrees. That's less than the width of your finger held at arm's length. At 12.3 billion miles, 2 degrees is the difference between a signal landing cleanly on a 230-foot dish in California and a signal vanishing into the dark between the stars, missing Earth entirely. The antenna moved, and Voyager 2 stopped talking. Engineers at JPL confirmed the loss of signal within hours. Data stopped flowing. Telemetry, the constant stream of numbers that tells mission control the spacecraft's health, temperature, power levels, instrument status, simply stopped arriving. They didn't know if the spacecraft was damaged. They didn't know if it was tumbling. They didn't know if the 2-degree error would compound over time, drifting the antenna further away from Earth with every hour that passed. What they did know was the schedule. Voyager 2 was programmed to automatically reset its antenna orientation as a failsafe, but not until October 15th, nearly 3 months away. 3 months of silence or a fix, whichever came first. Stay with me, because this is where it gets strange. You'd think, with a problem this precise, a 2-degree miscalculation, the fix would be simple. Just recalculate, resend the command, realign the antenna, except you cannot send a course correction to something that cannot hear you. Voyager 2's ability to receive commands from Earth depends entirely on that same antenna being pointed at Earth. The moment it drifted off axis, the spacecraft lost its ability to receive new instructions just as completely as it lost its ability to send them. It was a closed loop with the connection severed on both ends. JPL's engineering team, led by Mission Operations Manager Linda Spilker, who has worked on the Voyager program since 1977, faced a problem with almost no precedent. There was no simple resend, there was no backup channel, there was only distance, silence, and a spacecraft that might drift further from alignment with every passing day. On August 1st, 2023, the Deep Space Network's largest dish, the 70-meter antenna at the Deep Space Station in Canberra, Australia, was assigned to attempt something engineers internally began calling the Interstellar Shout. The idea, instead of a precisely targeted signal, JPL would use the Canberra dish to broadcast an extraordinarily high-powered wide-beam command in the general direction of Voyager 2's expected position, essentially betting that raw power could compensate for imprecise aim. The signal would need to travel 12.3 billion miles, arrive close enough to Voyager 2's misaligned antenna to be detected at all, be recognized correctly by 1970s-era onboard computer systems with less processing power than a modern calculator, and trigger a reorientation, all without any confirmation that any of it was working, until a response light hours later. Anomaly 1. Nobody knew if the failsafe systems built in the 1970s would even still function correctly after 46 years in the radiation and cold of interstellar space. Anomaly 2. Even if the shout reached Voyager 2, there was no way to know whether the spacecraft was healthy enough to execute it. If the malfunction was mechanical rather than a simple command error, the antenna might not move at all. The Canberra dish transmitted the command on August 1st. Then Mission Control did the only thing left to do. They waited. Radio signals travel at 186,000 miles per second. Even at that speed, the message took over 18 hours to reach Voyager 2's last known position. Then, if everything worked, Voyager 2's response would take another 18 hours to return. 37 hours minimum before anyone would know if a 46-year-old machine further from home than anything humans have ever built had heard a shout across the dark and turned to listen. Meanwhile, back on Earth, something else was happening that most headlines from that week didn't mention. Voyager 1, the twin spacecraft, technically slightly further from Earth than Voyager 2 despite launching second, began transmitting garbled, nonsensical data of its own in November of that same year, an entirely separate malfunction involving a corrupted computer chip. Two of humanity's most irreplaceable machines, both edging toward failure 4 months apart, both older than most of the engineers now responsible for saving them. It's the kind of coincidence that invites bigger theories. Dr. Suzanne Dodd, project manager for the Voyager program, has spent decades studying just how close to failure both spacecraft constantly operate. In interviews around this period, she noted that every year the team loses a little more capability, instruments switched off permanently to conserve the shrinking output of the plutonium power source both spacecraft rely on. Voyager 2's radioisotope thermoelectric generator has been losing about 4 watts of power per year since launch. By 2023, it had less than half the electrical power it started with in 1977. There are scientists, a minority but vocal ones, who've suggested online that these near-simultaneous failures across both spacecraft, decades into a mission nobody expected to last this long, hint at something beyond simple hardware fatigue. Cumulative, unpredictable effects of prolonged exposure to interstellar radiation on electronics never designed to survive this environment for this long, effects modern engineering has almost no real data on, because nothing human-made has ever been out here long enough to study. It's a real open question in aerospace engineering circles. Nobody knows exactly how spacecraft electronics behave after half a century in interstellar space because it has genuinely never happened before now. But mainstream mission engineers, including Dodd herself, have been careful to ground the excitement. The July 2023 incident wasn't cosmic radiation. It wasn't an unknown force. It was traced to something almost mundane, a scheduled command sequence with a calculation error sent by humans at Deep Space Network Station 43 in Canberra as part of otherwise routine spacecraft maintenance. Sometimes the terrifying silence has a boring human explanation that doesn't make the 37-hour wait any less agonizing. On August 2nd, JPL engineers monitored the Deep Space Network's receivers, watching for the faintest possible carrier signal, not even data yet, just confirmation that Voyager 2's transmitter was pointed somewhere close enough to Earth to be detected at all. Nothing. The window when a response should have arrived came and went. Every extra hour of silence deepened a specific kind of dread among the team. Not panic, mission engineers don't operate that way, but a quiet recalculation of probability, updated hour by hour, of whether this shout across 12 billion miles had simply missed, the way an actual shout might miss someone standing just around a corner. Then, on August 4th, at Deep Space Station 43 in Canberra, a signal appeared. Faint. Fragmented, but there, a carrier wave, and after it the first fragments of coherent telemetry in 14 days. Voyager 2 had heard the shout. The antenna had moved. The spacecraft, 46 years old, further from home than anything built by human hands, had received a command sent across 12.3 billion miles with imprecise aim and impossible odds, and it had obeyed. Everything changed in that moment, at least for the team watching the data stream refill with numbers again. Full data confirmed the spacecraft was healthy. Instruments intact. Power levels stable, consistent with the slow expected decline, no damage, no drift beyond the original 2-degree error. The fail-safe systems, dormant for decades, had simply been waiting to be called on, exactly as engineers in 1977 designed them to. It had worked entirely because of a design decision made nearly half a century earlier by engineers who could not have known when or if it would ever be needed. A fail-safe reset scheduled for mid-October as backup, quietly rendered unnecessary by an interstellar shout that reached its target 11 weeks early. You need to understand what this actually means. Voyager 2 is not simply old hardware drifting through empty space. It is the furthest continuous line of communication humanity has ever maintained. A live, two-way functioning relationship with a machine that left Earth before most of the people currently operating it were born. Every signal it sends now carries information no other instrument can gather. direct, in-place measurements of the interstellar medium, the actual physical conditions of the space between stars, not modeled, not inferred, measured in real time from inside it. There is no scheduled successor, no mission currently planned to replace what Voyager 2 does. When its power finally runs out, expected sometime in the early 2030s, as the last instruments are switched off one by one to conserve dwindling wattage, humanity's only direct physical presence in interstellar space, for a very long time afterward, will go silent for good. The July 2023 near loss was a preview, a 46-day glimpse of what that eventual silence will feel like, except this time, it ended with the antenna turning back toward home. It won't always. And that's the wide lens question this leaves behind, not whether Voyager 2 will eventually go quiet, every calculation confirms it will, but what happens to the story we tell about ourselves once the only voice we've ever had this far from home stops answering. Right now, the plaque bolted to Voyager 2's frame still carries the same message it left with in 1977, a diagram of our solar system, instructions for playing the golden record sealed alongside it, greetings recorded in 55 languages, addressed to nobody in particular, on the chance that someday, somewhere, someone might find it and understand it was never really about being found. It was about proving we tried to speak. For now, it's still listening, still answering, faintly, 45 seconds slower than light should ever feel patient, 45 seconds slower than it takes you to read this sentence out loud. Somewhere out past the edge of everything familiar, a machine built in 1977 is still turning its antenna toward a pale blue dot it left behind before most of us were born, waiting for the next thing we ask it to do. The dish that saved Voyager 2, the 70-meter antenna at Deep Space Station 43 in Canberra, is not just large. It is, quite literally, irreplaceable in the short term. It is the only dish on Earth with enough transmitting power to reach Voyager 2 at all, not one of several options, not a redundant system with backups spread across continents, the only one. There are two other deep space complexes, one in Goldstone, California, one in Madrid, Spain, each built during the Cold War space race, each designed to give NASA continuous contact with distant spacecraft as the Earth rotates beneath them. But only the Canberra dish sits in the right hemisphere, angled correctly, to talk to a spacecraft as far south in the sky as Voyager 2 currently appears. If anything had happened to that single dish during the exact window it was needed, a storm, a mechanical fault, scheduled maintenance that couldn't be delayed, there would have been no alternative, no backup shout, just silence, continuing indefinitely, until the automatic reset in October, if the drift hadn't worsened by then. This isn't a hypothetical. It very nearly happened before. In March 2020, that same Canberra dish went offline for scheduled upgrades, new transmitters, new receivers, work that had been planned for years and could not simply be postponed to suit a spacecraft's schedule. For nearly 11 months, Voyager 2 could still send data down to Earth, picked up faintly by smaller dishes elsewhere, but it could not receive commands at all. If anything had gone wrong with the spacecraft during that window, any malfunction requiring a human response, there would have been no way to intervene. Nothing did go wrong. The dish came back online in February 2021, full two-way contact resumed, and the 11-month blackout became a footnote instead of a headline. But it's worth sitting with what that means. For nearly a year, humanity's most distant machine was flying blind, deaf to anything we might have needed to tell it, kept alive purely by the fact that nothing happened to go wrong. When researchers looked again at the July 2023 incident with that history in mind, the coincidence became harder to ignore. The same dish, the same irreplaceable link. Twice in 3 years, the entire future of a 46-year-old mission had quietly balanced on the health of one piece of Cold War-era infrastructure, half a world away from the spacecraft it exists to serve. There is no second Canberra, not yet. NASA has discussed building additional large aperture dishes capable of Southern Hemisphere deep space communication, but nothing currently under construction would be ready before Voyager 2's power runs out entirely. Which brings the story back to that plaque, bolted to the spacecraft's frame since before it left Earth. The full message Voyager 2 carries is more elaborate than most people realize. It isn't just a diagram. Sealed on board is the golden record, a gold-plated copper phonograph disc containing 116 images encoded as sound, greetings spoken in 55 languages, 90 minutes of music spanning cultures and centuries, and recordings of Earth itself. Wind, thunder, footsteps, a mother's kiss, a human heartbeat. It was assembled in 1977 by a committee led by astronomer Carl Sagan, working under a deadline of weeks, not years, to decide what a civilization's entire self-portrait should contain if it only got to send one. The record includes instructions, etched directly onto its cover for how to play it, a diagram explaining rotational speed, stylus placement, even a source showing how to locate Earth relative to a set of nearby pulsars, cosmic lighthouses whose precise, unchanging rhythms could theoretically be used to calculate our exact position in the galaxy, thousands or millions of years from now, long after every landmark we'd recognize has changed beyond recognition. Sagan himself, in the years before the Voyager launches, described the odds of the record ever being found and understood as vanishingly small, closer to zero than to any meaningful probability. He said the point was never really about the odds. It was about the act of trying. That's the part worth remembering when a 2-degree miscalculation nearly ended the conversation 46 years into it. Every hour of that 46-day silence in the summer of 2023 wasn't just an engineering problem. It was the closest humanity has ever come to losing its only working line of communication with the part of itself that left home and kept going, carrying, on a small gold disc, the entire argument for why we bothered reaching this far in the first place. The antenna turned back toward Earth on August 4th. The data started flowing again. And 45 seconds behind everything happening right now, somewhere past the edge of the solar wind, a machine built by people who are mostly retired or gone is still doing exactly what it was built to do, listening, and when it can, answering. If you want to know what happens when it finally stops, and what NASA is quietly planning for the day that conversation ends for good, that's the next story.